So we're going to continue with convolution here. And so let's just summarize what we've seen. The input is simply a continuum of scaled impulses. That's the first idea. The impulses cause an impulse response. So each one of these impulses causes an impulse response. And then we add them all up via integration. That's what that convolution equation is doing. All right. And in doing that, we have this flip and slide of the input. All right. So let's try to visualize this a little bit. So here's what we're going to do. So here's going to be an input. It's a string of two impulses. So at time 0, I have an impulse of strength 1. And then at time 2, I have an impulse of strength 2. Okay. And I want to visualize what's happening. So common sense tells us that at time 0, once I have my system, since this is the impulse of strength 1, I will get an impulse response. I will get just a normal unit impulse response. This has strength 2, so starting at time 1, I will get another impulse response that's basically double of what this one is. Okay, so now we need the system impulse response. So I mentioned working for GM. You have to go out, go hit the train with a sledgehammer and a bunch of accelerometers and measure the impulse response. All right. And so let's say we did that. And we have, and I did this so I could draw things easily, but so we go out, we have a sensor, we hit some object, and the sensor records what we get. So at time we hit it, and at the moment it hits, it goes up over 1 second, goes up to 2 units or whatever, and then over the next second it goes back down to 0. Now nothing would respond to that, but this is for educational purposes. It's easy to draw and we can make that happen. We'll just put in a t time. All right. So let's think what it would be happening at time t equal 1/2 of a second. This is real important. All right. Don't read this yet. So here's what we have. We take this input, flip it at 0. I want to know what happens at 1/2 a second. So then once I flip it, I slide it to 1/2 second. So at 1/2 second, 1/2 of a second after I made my initial hit, all right, that first input is now 1/2 of a second into the impulse response. So it's exciting this part of the impulse response. This next impulse hasn't happened yet. It's outside of this. All right. So our impulse equation, when we looked at what we had, I'll write that over here, was integrate from 0 to t, I of t minus tau, s of tau, d tau. So in this case, we said, what's happening at 1/2 a second? So it's integral 0 to 1/2, we have 1/2 minus tau. And that's what this all is. At I of 1/2 minus tau, the initial input is here, and the second input is 1/2 a second out from occurring. All right. Then we have s of tau, that's the impulse response. Okay, so this says, take this, we've plotted these two, multiply by this. All right, so if I let this just extend out, this impulse response is, prior to anything happening, was 0, and then it goes out to 2, and then everything stops. All right, so if I multiply this by this input, here I have no impulse response, 0 times the impulse gives 0. I have no input here at 1/4 of a second. Therefore, there's nothing exciting this. All right. If I multiply this together and integrate it, all right, I am going to get the sifting function, which is going to bring out whatever the impulse response is at 1/2. Okay. And that's what this is talking about. So this shows the impulse response that's for an impulse that occurs at t equals 0, it is now exciting the part that's 1/2 in, and the second impulse is still 1/2 a second away. So if I were to plot this, what would I get? Just 1/2, or let's see, this is a height of 2, all right? So at time equal to 1/2, the height here is 1. So that would be the output right here. All right. Now, let's think of 3.5 seconds, or whoops, 3/2 of a second. That'd be right here. All right. So when we're 3/2 of a second into our response, so at time 0, we bang the thing with a sledgehammer. 1.5 seconds later, the initial impulse is this far in. At time equal to 1 second, the second impulse happens, but we've now gone 1/2 a second in. So this thing of strength 2 is exciting this part of the impulse response. So whereas this thing, when it was here, gave a 1, this will now double that and be an output of 2. Okay, let's look at 3.5 seconds. The impulse response just lasts for 2. So after 3.5 seconds, here's our initial input that's all the way out here, and it has nothing to excite from the impulse response. And here at 5.5 seconds, what do we have? Well, this one's a 1/2 second out. It's done its thing. It's shot its wad. It's over. Okay? So by drawing this, what we're seeing is we're going to draw I of t minus tau so we can see where all the inputs are on top of the impulse response. We multiply them together and take the area of what's left over. That's what the integral, this crazy integral says. All right? And then we add it all up. All right. So let's kind of go over here. What are our keys? Convolution reflects how a system actually physically responds to an input. The first input excites it first. Not a very profound statement. And it proceeds to excite the full the full impulse response. The second input then excites one after that, so on and so forth. And the inputs just slide through. This is the way a system actually responds. Okay, this means if you can record a calibrated impulse and impulse response, you can use that to predict/model the response for more practical inputs, like a step input, a sinusoidal input. Once you know the impulse response, that integral applies. All right, and here's the thing that's important. This would be called heuristic modeling, where you're actually using the actual machine and getting it and looking at its responses to determine what its models are. This is far easier and, quite frankly, far more accurate in the real world for modeling, rather than going from fundamentals and trying to derive an ordinary differential equation. This is used in so many ways. And we're just talking about impulse response. There are other approaches, okay? This is a tremendous way of validating models, developing models. And when I was at GM, this is what we did, okay? And it was very effective, very fast, because if you wanted to model something with an ordinary differential equation, you would have hundreds and hundreds and hundreds of orders that you would have to deal with. And in this way, you can basically see the dominant part of the model and then just do a fit to all of that and accomplish something much more quickly and very accurately, and it worked. Okay, this is really cool. So in one sense, here I am about to teach you a course where we'll eventually be modeling things. There is some dubious level of value in what we're doing, to be perfectly honest. Okay. However, if you're going to work with differential equations and eventually fit differential equations to it, you need to have and understand all the math that we do, totally relevant, totally 100% relevant. You can't dismiss any of that. But in general, you still need to know when you go to model things, what's the general effect of mass, of stiffness, of friction, of electrical components, this, that, and the other thing. So while you may not be doing multiple 100-order models of stuff, you will still, the intuition and understanding the effects of the various components is still very important. So that's why we do this, but we will note there are some limitations and applicability. And again, I wrote these notes ahead of time, but I worked at General Motors, and we've just had a little story time today. It was the best job ever. By the way, one of the things we did back then, just to finish up this video here, was in that day compared to now, well, what to say, what do we do now? These days we have incredible software modeling packages where we can actually, without having to go and put a lot of sensors on stuff, we can effectively do many types of the testing that we did just in software. And then you can just go do tests for calibration and stuff on the actual machines to verify it. So we have really powerful tools today for doing this. Excuse me. But back in my day, way back when, we didn't have these tools, so they had to build prototypes so that we could do testing on them to determine models. And back at that time, the insurance company, well, GM would build prototypes that they would send out to the various railroads, that they would literally do test driving and just decide if they liked something, give recommendations for approved design, would be a basis of them, buying locomotives from General Motors. However, the rules of these prototypes were they were not allowed to be sold. And so as a result, what would happen is the prototypes would come into the testing division, and we would then use them for various levels of testing, for improving the models. And as changes were done to the locomotives, people would recommend changes. So different prototypes, they evolved. And so we would have to recheck the models and stuff like that. But they weren't allowed to be sold. And so we had to get rid of these locomotives. And to do that, we would then do destructive testing. And I don't have if you look in the background, I have some trains in my office, but I don't have a modern diesel sitting here. But one of the things we did, so picture, suppose this, here's my mouse, suppose that was a diesel locomotive that nobody needed anymore. And we'd done all the testing we had to do to it. So now we had to get rid of it. So here's one of the tests that we did. An engine was brought into a test bay. And these bays are massive, like 100 feet long, 30, 40 feet high, I don't know, very wide. We literally took the engine, turned it upside down, and then bam, dropped it on the ground. You might go, why would you do that? Well, this was a way of modeling crash testing. Because if you ever watch railroads, actually the tracks are, you have the ground, and then, you have these things that are kind of high up. And so you have the tracks. So the idea is that the train could fall, if it had a derailment, it could fall over. So we modeled that, instrumented the whole thing up. And at the end of that, the engine was picked up, flipped back over. All of the destroyed parts were taken and, I presume, landfilled. I never really asked where the stuff went. At the time, didn't care, I guess. But then the pieces of equipment that still worked, we then proceeded to do more destructive testing. One of the tests we did in my time there that I remember was the first one I got to see. So this was really exciting. So we had a turbocharger off of a locomotive that had just been dropped, and it was still functional. So what we did is we put it on a test stand, and so there's a motor that could spin this thing up to 10, 20,000 RPM. I don't remember how fast those things spun. And we actually had some plastic explosives. We put it on the edge of the turbocharger. It basically looks like a turbo fan on a plane. So if you've seen a jet airplane, put a little explosive charge there, and then they welded a super fine wire going down, and it came out, and we had a slip ring, and it went out. And then this all got set up, and then so you get a picture the shaft is coming out to spin this thing up. Okay, but then we had this shroud that went over all of this. So we spun it all up to speed, had the shroud over it, and when it got up to speed, this was early in my time there, the person who was in charge of this experiment was like, you want to press the button? Hell yeah. So boom, boom. Anyway, the shroud, which was like, let's see it was maybe approaching a couple inches of thick. You couldn't pick it up. There, we had a device there that would pull that thing up. It had a loop on, so we had an overhead gantry and could pick that thing up. It had welts all over it. When we picked it up, it was just dust inside. And at the end of near the end of the day, my boss uh, asked me if we'd done the test, and I said, "Yeah, we did it." And he goes, "How much equipment did we lose?" And I said, "Well, the slip ring was totally destroyed. We finished all the remaining channels on it. So we actually got several explosions out of one slip ring, which was used to take the signals in off of the stuff that was blowing up. So we finished destroying the slip ring and some other various parts. And so I told him there was about I don't remember the number, 50, 60, $70,000 of lost equipment. And he goes, "Oh, no problem. Just make sure you reorder the stuff before you leave today." No problem. It was the greatest job in the world, because if you ever made a mistake, you just included your mistake in the stuff you blew up the next week, and all the evidence was gone. It was a fun job. And with that, I bid you well.